Assalamu alaikum. Myself Dr. Ansari Farzana, Sama, Department of Chemistry, J.A.T. Senior College, Malegaon. Welcome all of you. Real solution of miscible liquid. Most of the solution do not behave ideally, show some positive deviation and negative deviation from Raoult's law. This solution do not obey Raoult's law for all composition. Delta H mixing and delta V mixing for them is non-zero. There are two types of the deviation. System with positive deviation. It corresponds to the case in which the interaction between unlike molecule A and B are weaker than those between like molecule AA-BB. Hence, there is a greater tendency for the molecule to leave the solution than in case of ideal solution. Consequently, the vapor pressure of the solution is greater than the pressure expected for ideal solution, and delta H mixing is greater than 0 and delta V mixing is greater than 0. See here the vapor pressure of the system with positive and negative deviation. Positive deviation, for example, cyclohexane carbon tetrachloride. Positive deviation with maximum positive deviation. For example, in case of methyl alcohol and carbon disulfide, there may be chance of positive deviation with maxima, negative deviation with minima. Examples are acetone and chloroform. There are two types in this case. Type first, in this case, total vapor pressure as well as partial pressure exhibit positive deviation from Raoult's law, but the total pressure is all time intermediate between the vapor pressure of the two pure component as shown in figure A. In type second, in this type, the total vapor pressure as well as partial pressure exhibit positive deviation from Raoult's law. The total pressure passes through the maximum with change in composition. The maximum vapor pressure is higher than the vapor pressure of either of the pure component. Such systems are called azeotropic mixture with maximum vapor pressure as shown in figure B. System with negative deviation. It corresponds to the case in which interaction between unlike molecule A, B are stronger than those between like molecule AA, BB. Hence, there is less tendency for these molecules to leave the solution than in case of ideal solution. Consequently, vapor pressure of the solution is less than the vapor pressure than the pressure expected for an ideal solution, and delta H mixing is less than 0 as well as delta V mixing is less than 0. In type third, the total vapor pressure as well as shown in the figure C, the total vapor pressure as well as the partial pressure exhibit negative deviation from Raoult's law. The total vapor pressure passes through a minimum with change in composition. The minimum vapor pressure is lower than the vapor pressure of either of pure component. Such systems are called azeotropic mixture with minimum vapor pressure. See in the figure C. Example of the negative deviation with minimum vapor pressure is acetone and chloroform pair water and nitric acid pair, pyridine and acetic acid pair. Vapor pressure diagram of miscible binary mixture. On the basis of diagram as shown in figure, as shown in this figure, in this figure. On the basis of diagram in this figure, all miscible liquid pair can be classified into the three types. First type is the system whose total vapor pressure is intermediate between those of pure component. System whose total vapor pressure is intermediate between those of pure component. And second one is the system exhibiting a maximum in the total vapor pressure curve. System exhibiting a minimum in total vapor pressure curve. The vapor pressure liquid composition curve and vapor pressure vapor composition curve of the three type it is illustrated in this in the figure. See here, from the figure it is concluded that for all type of vapor composition curve lie below the liquid composition curve. In type second and third, liquid composition curve and vapor composition curve meet at the point of maximum C and minimum D vapor pressure respectively. At point C and D, composition of solution and vapor pressure and vapor are the identical. The diagram of the type second may be considered as being composed of two curves of type first, one for pure A and the solution of maximum vapor pressure C and other solution of the maximum vapor pressure C and B. The diagram of type third may be considered as being composed of two curves of type first, one of pure A and solution of minimum vapor pressure D and other of solution of minimum vapor pressure D and pure B. At a given temperature, the vapor pressure of pure B is larger than that of pure A. The liquid B volatilizes to greater extent than the liquid A. In figure A, the liquid composition and vapor composition curve are both continuous and at all concentration the composition in the two phases are different. As B is more volatile than A, the vapor pressure is richer in B than the solution phase for concentration of solution A. Liquid mixture of composition A will be equilibrium with vapor pressure composition. In composition with A and A dash lies closer to B. Thus, the vapor pressure is richer in component here B, which is more volatile. The, the same explanation may be offered to all mixture A and C in type second. For this reason, all mixture between A and C must have vapor richer in B than solution phase. The liquid of composition in equilibrium with vapor composition and in comparison with B, the point B dash lie closer to capital B. Also, mixture between C and B have vapor richer in A than solution phase. The liquid of composition C is in equilibrium with vapor of the composition small c dash and in comparison with small c, the point C dash lies closer to capital A. The same explanation may be offered to all mixture between A and D in type third, that means in C, figure C. And all mixture in this region must have vapor richer in A than solution phase. The liquid of composition small d is in equilibrium with vapor pressure composition small a dash, E dash, and in comparison with D, point A dash lie closer to A. Also, mixture between D and B have vapor pressure richer in B than the solution phase. The liquid composition and in comparison with E, the point E dash lie closer to B. Boiling point diagram of miscible binary mixture. In the three type of vapor pressure diagram discussed in previous section, the temperature is constant. From the discussion, it is clear that vapor above any solution is always richer in more volatile component than the solution. Thus, component of solution can be easily separated. The solution can be made richer in less volatile component by removing the vapor above solution. If the vapor is condensed, a solution with another composition is formed. The vapor above the solution again considerably richer in more volatile component than the solution. By repeating this process, it is possible to concentrate more volatile constituent in vapor and less volatile constituent in the solution. This process of concentrating the component is called isothermal fractional distillation as the process takes at constant temperature. Instead of conducting distillation at constant temperature, in practice it is much more convenient to conduct the distillation at constant pressure. The boiling point of solution is the temperature at which total vapor pressure become equal to external pressure. Thus, the solution of two components A and B will boil when P is equal to PA and PB, PA plus PB is equal to atmospheric pressure. This is the simple type of boiling point distillation diagram corresponding to various vapor pressure diagram. According to Raoult's law, different composition of a solution have pressure. Therefore, it follows that solution of different composition will boil at different temperature. The solution whose component more volatile have high will boil at a lower temperature than the solution in which the component have lower vapor pressure. It is possible to construct a boiling point diagram, vapor pressure diagram. These diagrams are illustrated in previous figure. In type first, in type first, the vapor pressure of pure A is lower than that of pure B is the highest, while the vapor pressure of all composition of A and B lie in between two. Therefore, in the boiling point diagram, the boiling point of A is highest and that of B is lowest, while the boiling point of all components of A and B lie in between two. The decrease in boiling points with composition is continuous as we move from A to pure B and from A to B. Similar explanation can be offered for type second and type third. Thank you for watching.